So in this video I'm going to talk a bit about the moments and how they affect objects. So first of all, what is moment? It's basically a force that's trying to cause an object to rotate. So you've seen before how you can have forces acting on objects and they can cause them to accelerate. Well, they can also cause them to rotate as well, and that's what a moment's all about. So you can calculate a moment by knowing the force that's trying to cause an object to turn and the perpendicular distance between that force and the centre of rotation. So, putting that into a bit more detail, you might often come across systems which are in equilibrium, and there are two key conditions you need to know about for a system to be in equilibrium. So first of all, the resultant force acting on an object must be zero. So if we take an object, say a beam like this, you know it's going to have its weight force acting down there, and maybe it's going to be supported at either end by F1 and F2. So you know that if it's going to be in equilibrium, the forces up must equal the forces down. So F1 plus F2 is going to be equal to the weight force, or the mass times g, whichever way you want to express it. So that's showing the resultant force being zero in these two conditions, so the force up is equal to the force down. So let's have a look at a moment example. So say this time we've got a beam like this again, and we're going to fix it at this point here, and I'll call that A just for simplicity. And then again we're going to have its weight force acting here, and we want to know what force we need to apply at this end here. So let's add some dimensions in. So let's call this D, and if this is a uniform mass distribution, you know that the weights can act at D over 2, although the diagram looks a bit wonky. So let's set up the conditions for it to be in equilibrium moments-wise. So let's have a look at the clockwise type moment, so the moment's going around this way. So you've got the weight force, W, and then multiplied by the perpendicular distance. So if the force is acting downwards, the perpendicular distance would be at 90 degrees. So we're looking at this distance along here, which is going to be D over 2. And now if we look at the counterclockwise or anti-clockwise moments, we've got the force, F1, and the perpendicular distance in this case is nice and simple, so it's D. So the condition to be in equilibrium is that the force times distance, so the supporting force times the distance, is going to be equal to WD over 2. So that will be the conditions for moments to be, or the resultant moment to be zero in that case. So let's move on. So in the last example we looked at something which is fairly simple, but what we're going to get onto is looking at, well, what if the forces are applied at angles? How do we deal with that? So with these ones here, so if in both of these cases we're going to say the centre of rotation is this point A at each end. This one at the top is nice and easy because the forces are acting downwards. So the perpendicular distance between the pivot, or the centre of rotation, is just going to be these distances here and this distance here. So it's always from the pivot at 90 degrees to the force. That's nice and simple. But if we look at this bottom case here, where we've got a force applied at an angle. So let's just mark in the lines. I'm going to say it's applied at this angle theta here. So in order to thinking about perpendicular distances, we need to try and resolve this force into two directions. So if we model it as being a force like that and a force like that, where this force is going to be F times the cosine of theta, and this one here is going to be F sine theta. And again, let's put in the distances here. So we're going to call this D. So if we think about the moments going clockwise around this way, we have this force here is now being applied vertically, so its perpendicular distance is D. So you've got the force, which has this magnitude here, so that is your force part, times the perpendicular distance, which is D. Now if we look at this other force over here, the F cosine of theta, and we look at the perpendicular distance of the force from the center of it, you'll see that it's actually in line with this one here. So its perpendicular distance is actually 0. So if it had been applied up here, you'd have had a perpendicular distance like this, but there is actually a distance in here of 0. So the F cosine of theta term doesn't have a turning effect in this case. So its magnitude is 0. So you just have this moment acting on this object here. Okay, so let's put this all into practice in a worked example. So we have a scenario you might come across. So we've got a drawbridge attached to a castle. So we've got a hinge at point A, so let's mark in where that is. So that's there. The rope is connected at point B, which is here. And this length, it tells you, is 6 meters up here. So you've got a force of 200 G acting there. We've got 4,000 G acting there. We've got this distance here, 10 meters. We've got this distance here of 3 meters. And that is all the information given there. So before we even try and do this, a couple of things to spot. So you've been given 2 lengths of a right-angled triangle, which means should you want to, you could work out what this length is here, and it also means you can work out either of these 2 angles here, which will become important later on. But currently, this diagram is going completely bonkers. We want to try and represent it just in terms of this beam here. So what I want to do first of all is, if we're going to look at the tension in the rope, so if you think this is your rope, we're going to need to know the angle between that there, because we're going to need to use that later on. So let's work out what that angle is. So we're looking at this angle here, theta. We've got the opposite and we've got the adjacent side. So if we've got that, the only thing we've got left is, so opposite, so 6 divided by 10, which means that you could work out your theta as being the inverse tangent of 6 over 10. So we have an expression for this angle here, which we can then use later on. So let's set this up in a useful diagram. So this is a way of showing the different forces that are acting on the drawbridge. So we need to think about looking at the moments here, because remember, there are going to be, if there's a pivot here, there's going to be support forces which we don't know in this example. So we're going to need to use a moments case to work out the tension, because there are forces we don't know. So if you take moments about A, let's first of all have a look at the clockwise moments. So we've got your 200g multiplied by its perpendicular distance, so that would be this 3 meters. We've got this 4000g, so the centre of mass of your drawbridge, multiplied by 5. Now the tension of the rope is going to have two components, so it's going to have a component in that direction and a component in that direction. So the vertical component is going to have a counterclockwise moment, so we're not going to consider that. And the horizontal component has 0 perpendicular distance between it and the A, so that's not going to have any effect at all in this problem. So we've got our expression for the clockwise moments. Let's look at the anti-clockwise moments. We've got the tension in the rope, which is supplying the force, T. We need the vertical component, so we're going to multiply it by sine of theta. And we need its perpendicular distance, so we know that's 10 meters. So in order to be in equilibrium, as it says in the question, you know that the moments have to cancel each other out, and you get left with this expression here. So let's do some simplification before we move on anywhere here. So we want to get to this t sine theta expression, so if we multiply out this first term, we'd get 600g, cancel the 10, leaves you with 60g, and on the second time here, 4,000 times 5 would give you 20,000, cancel the 10, gives you 2,000g, which is going to be equal to 2,060g. So the final step, we want to calculate t. Got our expression here, and if we remember from earlier, we had our expression for that angle, so of 6/10, which you can work through, which gives you 39278.46. And remembering tension is a force, so it's going to have the unit of newtons. So let's have a look at how many significant figures we should be using here. So in the original problem, you were given the masses were 200 and 4,000, which you could argue are 3 and 4 significant figures, so they're not going to be the limiting factor here. So the limiting factor is going to be the lengths that were given, which are both, and this 6 here is given to one significant figure. So you're using one significant figure, two significant figures, and then 3 and 4, and then G used 9.81, so that's 3 significant figures. So you can give your answer to one more than the smallest number, which would be 2 significant figures. So we'd round that to 39 kilonewtons there. It would also be absolutely correct to give the same number of significant figures as the smallest, so 40 kilonewtons. So either of those two answers would be absolutely fine for this question, and you calculated the tension in the rope.